Welcome. My name is Zichao Zhang. I'm going to present our work, Automating Compositional Analysis of Authentication Protocols. This is a joint work with my colleague Arthur and my advisor Li Mingjia and Karina Pasarun. Over the years, it has become evident that cryptographic protocols used in distributed systems for authentication and other purposes are prone to various kinds of design errors. Yet, those protocols form the cornerstone of security. To start, let's first talk about the well-known Needham-Shorter protocol, which intends to provide mutual authentications for two agents, Alice and Bob. Alice starts by contacting the server, asking for Bob's public key. The server returns this information to Alice, signed with his own secret key. Then, Alice encrypts the fresh nonce NA and sends it to Bob, along with her own identity. Bob asks the server for Alice's public key PKA and sends NA back to Alice, along with his own nonce NB, all encrypted with Alice's key. Finally, Alice acknowledges the end of handshake to Bob by sending him NB back, encrypted with Bob's public key. Informally, the rationale behind the protocol is that since only Bob can recover NA, when Alice receives message 6, she knows that Bob accepts her connection. Similarly, only Alice should be able to recover NB, so when Bob receives message 7, he knows that Alice has tried to contact him. However, this protocol is vulnerable to a man-in-the-middle attack, in which an attacker Charlie engages Alice in a session of the protocol, while in parallel is able to impersonate Alice in another session with Bob. Lowe fixed the protocol by including Bob's identity in message 6 from Bob to Alice. However, this protocol flaw had remained for 17 years before it was discovered. In fact, Needham and Shorter put a statement in their 17A paper saying that protocols such as those developed here are prone to extremely subtle errors that are unlikely to be detected in normal operations. And this spiked a line of research to formally verify the protocol. Since around 2000, many formal symbolic protocol verification tools, for example, Korev and Tamarin, have been developed and applied for various real-world protocols. Unfortunately, current techniques are monolithic, meaning the entire protocol is verified at once. And this introduces a lack of flexibilities and scalabilities. For example, during development, protocol usually goes through several drafts before the final version. However, if I only modify one component in the protocol, I will have to rerun the entire proof to check if the modification will break the security. And this motivates our work to try to modularly verify each component of the protocol. To illustrate, suppose we have a complex system composed of M1 and M2, and we would like to show the system satisfies the property P. Rather than proving P directly, we can use the following assumed guarantee rule, which says that we can prove P by finding an assumption Q, such as, first, P holds on M1, assuming that Q holds on the rest of the system. And second, the component M2 guarantees that Q holds. Well, it could be challenging to come up with the assumption Q by hand. Our work has shown that it can be inferred with an automaton learning algorithm called L-star. So L-star will learn the assumption using the so-called interface alphabet, which informally represents all communications between the two components that may influence each other's behavior. To apply assumed guarantee reasoning on cryptographic protocol, we developed Talarino, which includes an DSL to describe protocols and attacker behavior. This DSL supports many standard cryptographic constructs, such as symmetric encryption, digital signature, and so on. And because we use a bounded model checking, we have to bound the attacker behavior. And roughly speaking, we will sample a subset of messages to be exchanged by the attacker from all the possible messages that could appear in network. And finally, Talarino will compile the DSL down to finite state machine used for our backend model checking. Just to show an overview, we will carry out the first step where we try to generate assumptions. Protocol specifications are manually coded using the DSL, and Talarino will automatically compile it into models for our backend LTSA model checker extended with automated learning. We will also tell LTSA how do we want to decompose the system. For example, we could set M1 to be Bob, attacker, server, and M2 to be Alice in the rule shown in the previous slide, which will synthesize assumption on Alice if it exists. We will then reuse the assumption we got to check for protocol variants. Suppose we modify Alice in the protocol. We can then reuse the assumption generated previously to check if the modification will violate the property. For experiment, we used Talarino to generate models for NSL and its two variants. And we use NSL to generate assumptions. Recall that we used a bounded attacker, and this attacker, although finite, turned out to be huge. So we first generate assumption on the attacker using alphabet refinement. And roughly speaking, alphabet refinement will generate a more compact assumption by limiting the interface alphabet between the components. We then use the attacker assumption to generate assumption on Alice, and we use the assumption on Alice to check for protocol variants. The table shows the comparison of the original components with its generated assumptions. The generated assumptions are much smaller compared to the original one, and we show that verification becomes faster when we reuse the assumptions. We also try to interpret the generated assumption by inspecting its refined alphabet of the attacker. The assumption alphabet represents all actions that must be controlled by the property to hold. If you remove those actions from the alphabet, then the attacker can freely perform those actions without requiring enough knowledge to derive the message. We observe that most of the messages in attacker's alphabet are variants of the problematic message 6 encrypted with attacker's key. This makes sense because if the attacker can make up such messages out of the thin air, then he is capable of learning the nonce NB even before Bob is contacted, thus breaking the authentication. To conclude, we developed Talarino for analyzing authentication protocols. We evaluated on NSL and its two variants. We found that we could reduce verification costs when we want to reuse the assumption. And we could also interpret the assumptions to some degree. In the future, we plan to try out more case studies, and we also want to further interpret the assumption and maybe incorporate those in other verification tools. Thank you for your attention.